So the example that we will start with, though, is the storage tank is going, there's liquid in the storage tank that is being pumped through a positive displacement pump that's going through a flow meter that's going through an on-off valve that is then going into a main header or a storage tank or wherever else it needs to go. So there is a feedback from the flow meter back to the PD pump, and the PD pump is run by a variable frequency drive. So the raw material is dosed into the primary flow at a target flow rate, and so we'll be talking through how do we control to the target flow rate. The flow rate that is desired comes from a percentage in a formula or some other process design. So this is a close-up of an HMI. This is just a screenshot that I found on the web, and so picture in the upper left-hand corner, it says cold water. It says there's a flow rate and there's a target. So this process is not running, but at some point it will be running, and we want that flow rate to equal the target. And the operator knows what's happening by looking at this HMI, and they're reacting to alarms, and any input that the operator makes through the HMI gets passed through to the PLC, which is where the data then gets manipulated and converted into power that gets sent out to processes out in the field. So from the HMI, the information goes to the PLC. The PLC will be in racks, which are basically big electrical boxes that you'll see out in the field. And PLC stands for Programmable Logic Controller. There's a program that runs on the PLC. So the program is, which is the set of instructions that needs to happen for the process to be controlled correctly. The program defines when each pump, valve, or motor turns off or on, and it turns the operator instructions into actions in the field. So if a operator presses start on a process, and multiple pumps are supposed to start up at the same time, the PLC is what actually starts to send that signal to start off to the VFD. So the variable frequency drive is what converts both the on-off and the speed commands from the PLC into power for the pump's motor. So a pump is driven by a series of sinusoidal waves that the higher the frequency of the wave, the faster the pump is turning. And if there is no power going through, then the pump is not running. So the VFD is sending the power to the motor. The motor is then turning the pump. The pump is what actually pumps the liquid. So you can see that in the picture here that there's an inlet on the pump side. There's looks like a 3-inch triclover fitting. That is where your liquid will either be coming in or out of the pump. So we have liquid coming into the pump and out of the pump, and from the pump we are heading towards our final destination. But before we get there, we are measuring how much of the flow is actually there. And so for that we use a flow meter. There are different types. A very common type of brand is Micromotion, and it is a Coriolis flow meter, which is just a really cool concept that that people can figure out how to make this. There are two coils. There are two loops. These two flow paths are being forced to oscillate, but exactly how much they oscillate is an indication of how much flow is going through there. So these are very sensitive pieces of equipment that give very accurate indications of the flow rate going through there. So we know what the flow is, and the PLC has to make a decision. If the flow rate is too high, it will tell the VFD to slow down. If the flow rate is too low, then the PLC is going to tell the VFD. PLC is going to tell the VFD to speed up. So this is the feedback loop, not putting all the pieces together. And there are many different parameters that go into defining how this loop is tuned. If it's very far away, we could tell the VFD to react extremely fast. The risk there is that the flow rate will jump to the other side of the set point, and we end up just chasing our tail and end up just swinging back and forth